Hey, what is going on, guys, and welcome back. We are continuing. We're starting section 2 of part 5 in this video, covering references. Just a quick side note, I did post a video yesterday. It's a very, very short video. I think it's about like 2 minutes long. And in that video, I asked you guys how you would recommend or how you guys would prefer future videos are made, or I should say structured, for the remainder of the course. And I basically asked if you guys like this format in which I just read the material on screen, talk about the examples that we see, and explain some of these topics a little bit more in depth should, additional information be required, and then cover the exercises on the video as well. Or if you guys would prefer that I just have the videos cover only the exercises. So we won't do any of these readings. We'll just, the video will start off with me looking at the first exercise in this section, for example. We'll read the instructions, go over any provided test cases and whatnot. Then we'll jump on VS Code, do the exercise, submit the solution, talk about the model solution, then we move on to the next exercise, like that. So I'm just looking for some feedback, and so go check out that video. Let me know in the comments of that video what you guys would prefer that I do, or but for until I get a clear answer, I'll continue making videos the exact same way that we've been doing so far. We'll read the material on screen, and then we'll do the exercises in the same videos. If the videos go on too long, then we'll split them up into multiple videos. So yeah, so in this video, we're gonna do section 2 of part 5 on references. Learning objectives for this section is that you will know what is meant by a reference to a variable. You will understand that there can be multiple references to the same object. You will be able to use lists as parameters and functions, and you will know what is meant by a side effect of a function. This we've already explored multiple times since section 4 when we started learning about lists, and ever since we started writing functions, right? We've written plenty of functions that use lists as parameters. So I guess this will kind of cover that a little bit more in depth. But yeah, we've already covered this. I've also talked about references in programming. This section is just going to cover that a little bit more in depth. And again, as I mentioned at the beginning of the video, if anything needs further details that I think are important to share, coming from experience in prior, experience in the professional world as well as experience in a collegiate setting, I will, talk about that as the content shows up. So thus far, we have thought of a variable as a sort of a box which contains the value of the variable. Technically, this is not true in Python. Technically, this isn't true in programming, at least in most programming languages, maybe in assembly or some more machine-based programming languages, or focused as that are based. But yeah, this isn't technically true. What is stored in a variable is not the value per se, but a reference to the object, which is the actual value of the variable. And this is what I talked about, I think, either in the last video, the last actual video covering topics, the previous section on lists. The object can be a number, a string, or a list. So yeah, basically, when you have, let's go to the Python playground here in a second. So hopefully I've zoomed in quite enough. So in programming, but in this instance, we're talking about Python. So in Python, right, when I do name is equal to, I'll just use my name like this, right? Now, from what we've been learning so far is that our understanding sort of points us to conclude that this and this are one and the same, right? Like this exists because of this, or vice versa, right? Like these are, yeah, basically these are one and the same. So when we do print name, right, we think that we're printing the actual data type, right? We're actually printing this string. But instead what we're doing is the variable name is a reference to the data type. It's a reference to the actual data, right? This name, this variable name, is telling Python where to look in memory to find this data, this string, Stefan, right? That's what's happening here. Now this is what we call, is when we're calling a function and we pass the variable name, what we're doing is what's called passing by reference, right? We're pointing to the data of the string Stefan. We're not actually directly using the data, right? So when we do this, this is passing by value. We're passing the actual data type. We're passing the actual value that we want to be printed. So while these are doing the exact same thing, one, when we're using the variable name, we're pointing to it, or we're referencing where this data type is stored, versus actually using the data type. And in memory, these two are completely different, right? These two are completely different. They're not pointing to the exact same position in memory, right? There's now two Stefans, right? Strings that say Stefan in our memory somewhere, right? But one is, let's say for example, this is position 1000, or whatever, 1001455, right? But this could be position 1000126, right? They're not pointing to the exact same thing. So that's sort of the way you should be understanding now when we're programming. And this is pretty much the behavior across virtually every programming language. We're never actually, when we're using variables and we're calling these variables in functions, in loops and whatnot, we're not actually talking directly to the data. We're talking to the reference, right? We're talking to, I guess, like an instruction on where to find that data that we want to be printed, to be looped over, or whatnot. So that's what this is talking about. In practice, this means that actually I forgot, I should zoom in a little bit more. In practice, this means that the value of the variable is not stored in the variable itself, right? This is an even better way to put it. Instead, there is information about the location in computer memory where the value can be found, which is what I was just talking about. A reference is often represented by an arrow from the variable to the actual value in memory. So here we have the variable a, which points to this list of integers, and the integers are 1, 2, 3. So when we call a somewhere in our code, it's pointing to somewhere in memory where this list exists that has the items 1, 2, and 3. So reference tells us where the value can be found. The function ID can be used to find out the exact location the variables point to. Right? So this is really, really neat. I don't know if this exists. I'm pretty sure it exists in Java, in C++, and whatnot, but I just never really bothered to explore any further. But I think this is pretty cool. So we'll copy this so we can see it in action. Right? So when we say, right, variable A is here, right, is pointing to this list, this is where it is in memory, right? This is the ID. This is like the position in memory that this list that contains the values 1, 2, and 3 exists at, right? And variable B is assigned the reference to this string, right? This string that says this is a reference to. And when we use the ID function and pass our variable B, this is where this string is living in memory at this position, 139683447 blah, 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 right? So this is actually pretty cool to be able to see this in action. Now, again, what I'm curious about, would this work, for example, right? If I was to just do this, right? And it also works, as you can see, right? So we pass the same, another list that has the exact same values, right? But as you can see, they don't exist in the same location in memory. This list, right, our final print call here, exists at all the way up to, right? So these first 1, 2, 3, 4, 5, 6, 7, 8, like this, the first 8 digits are exactly the same in our three variable, in our three, in the 2 references and in the actual data type, right? The first 8 integers are exactly the same, but every integer after that is what differs. So that's how we can tell they're in completely different positions in memory. But this is a really, really nice functionality that's built into Python to basically further illustrate what this point is talking about, right? When we use variables, we're basically telling Python where to look in memory to find the data that we're talking about, right? So when we find this list that contains 1, 2, 3, right, and it's assigned to this variable A, And when we call it, this is where it is in memory. This is where the list 1, 2, 3 exists. But you can see when we have another list of 1, 2, 3, even though it's not assigned to a variable, right? Python creates an entirely new list. It doesn't look for if it exists somewhere else. And that's what sometimes when we talk about, you know, right. So even if we create a list that looks exactly like the one that's saved in reference here, they're completely pointing to two different things in memory because Python creates a new list now and saves that to memory. So when we talk about memory, what was the term? Sometimes it evades me, but it's like you're almost building up debt to whenever you create variables or create data types, right? Because they're always going to be stored somewhere, so you have to figure out a way to sort of wipe them away from memory so you don't end up building too much debt because you're going to be creating lists and references and whatnot that you might not end up using again in the future. So, that's why this is actually a pretty cool way to illustrate references in programming. So hopefully that makes sense. So yeah, so this is basically what we just covered. When we call the ID function, right, we can see that this list is pointing to this position in memory and variable B is pointing to this string, which exists in this position in memory. The reference or the ID of the variable is an integer, which can be thought of as the address in computer memory where the value of the variable is stored. If you execute the above code in your own computer, the result will likely be different. As your variables will point to different locations, the references will be different. The Python tutor visualization tool also shows references as arrows from the variables to the actual content, as we saw in the previous section. The tool cheats a bit when it comes to strings, however. It displays strings as if they are stored in the variables themselves. So when we put this code in the Python visualizer, right, and we print the ID for this variable, it's going to print this, but it's also going to print it as it's also like the ID is also a part of the string. In reality, Python strings are handled very much like lists with references to locations in memory. Many of the built-in types in Python, such as string, are immutable, right? Meaning we can't modify them. This means the value of the object or any part of it cannot change. The value can be replaced with a new value. So when we do myString and we point to this string hey, and then we do myString is equal to myString, and we concatenate this this exclamation point to it, then when we find the ID for myString, it's not going to point to the same position in memory that the string hey without the concatenation pointed to. It's going to create a new position in memory, and then it's going to reference that. Some of Python types are immutable. For example, the contents of the list can change without needing to create a whole new list. So here when we have the variable mylist, we point to the list of integers containing the values 1, 2, 3. So when we find where mylist is pointing to in memory and then mutate it, it'll still point to the same position in memory because lists are immutable or they're updatable, or we can traverse a list, we can update values at each index in the list, and the variable assigned to that list will continue to point directly to that list. It may surprise you that also the basic data types integer, float, and boolean are immutable in Python. Let's have a look at a bit of following code. Here we have a variable number. It points to the integer 1, assigned to the value 1. Number, again, is reassigned to the value 2, and then we do compound addition, and we add 10. It seems that the commands above are just changing the value stored in the variable, but in fact, each command creates a whole new number in the computer's memory. The printf from the following program illuminates the situation. So when we do number and set that equal to 1, and then we print the ID of number, it's going to print one position. Then we'll concatenate, we do compound addition, and we add 10 to number, and then print the ID of it again. It's not pointing to the same position. Now it's pointing to this new position that ends in 44 instead of ending in 12. And then when we set we'll create a new variable here, and we assign it this integer 1, and then we print the ID, right? This is now pointing to the original position that we set number equal to. At first, the variable number points to the memory location 453-585-6912. When number is assigned a new value, it points to the location 4535-856944. Now when the variable a is assigned the value 1, a points to the very same location where number was pointing when it was also assigned the value 1. It seems Python has stored the value 1 in the memory location 4535-856912 whenever a variable is assigned the value of 1. It refers to that location in computer memory. It is good to keep in mind that almost everything is a reference in Python, but also this is rarely relevant to everyday programming tasks. So let's get back to the more practical matters. Yeah, this is one of those things that's just really good to know, even though it might not be important per se, but if you care about, maybe if you're writing a really efficient program and you have a program that either reuses the same variable names and whatnot, this might be one of those things that could be good to know and test and see if you can make your program not create too many new positions in memory, if you want to make it completely efficient. But yeah, so this is basically the whole shebang that you need to know when it comes to references in programming. Multiple references to the same list. What actually happens when you assign a list variable to a new variable is the list copied over. Here when we have a variable a, which points to the integer lists for 1, 2, and 3, we have a variable b, which equals to reference of a. Then when we do b, and we target the index 0, and set that equal to 10, right? The assignment b equals a copies the value stored in variable a to the variable b. However, the value stored in a is not the list itself, but a reference to the list. So the assignment b equals a copies the reference, and as a result, there are now two references to the same memory location containing the list. So here, right, when we create a variable a and assign it as a reference to this list that contains these integers, and then we say b equal to a, then both b and a point to the same position in memory, right? So when we do b, when we mutate the first index in the list, then when we, both b and a will still point to that same position in memory, right? We basically don't create two positions in memory that point to similar lists. And then when we update the index using position 0 for the list using b, it's not pointing to a new position. They're pointing to the same position in memory. The list can be accessed through either of the two references. So when we do this, list 1 is equal to this list of integers. Then we set list 2 equal to list 1. And then we change the position of index 0 of list 1 to 10, and the position at index 1 of list 2 to 20, right? And then we print list 1 and list 2. They're going to print the exact same thing, right? Because they're pointing to the same position in memory. Here we're manipulating the exact same list, even though we created two different variables and assigned the list to reference to list 1 to variable list 2, right? They're still pointing to the same position in memory. If there's more than one reference to the same list, any one of the references can be used to access the list. On the other hand, a change made through any one of the references affects also the other references, as their target is the same. The visualization tool is very useful in figuring out what is happening. So I'm not going to go through this in the Python visualization tool, but you can in your own time and see what it does. But it's basically going to do the exact same thing that we just talked about. Another way you can do this is, again, if you just go to the Python playground, right? So if we were to do this, for example, then we were to do print ID of A and then print ID of B. As you can see, they're pointing to the exact same position in memory. Then if I was to do B0 is equal to 10 and A1 is equal to 12, and we print A and we print B, right? Prints the exact same thing. Then if I was to print the positions one more time, you'll see that they're pointing to the exact same positions in memory. So this is basically creating two references to the same data. And we can update that list whichever way we want, with either reference, and the list will still update and it will still point to the exact position, same position in memory. If you want to create an actual separate copy of a list, you can create a new list and add each item from the original list in turn. So here we create a variable called myList, set it equal to this, pointed to this list of integers, create a variable called newList, set that equal to an empty list, and then for item in myList, newList that append that item. So now newList and myList will have lists that look the same, but will point to different positions in memory. So when we change newList 10, first index of newList to 10, then the list will have 10, 2, 3, 3, 5. When we append 6, then newList is going to have 10, 2, 3, 3, 5, 6. As you can see it printed down here. Again, this is the Python visualizer screenshot. You can copy the code and put it through the Python visualizer and it will help you see everything, but I'm not going to do that in this video. If you prefer that I do this in the future, more in depth, whenever we cover new topics, let me know. I'd be happy to spend extra time putting the examples through the Python visualizer and going step by step to see what's happening when the code is being executed. The variable newList points to a different list than the variable myList. An easier way to copy a list is using the bracket operator, which can be used for slices previously. The notation selects all items. The notations of using open bracket followed by colon followed by closing bracket selects all items in the collections. As a side effect, it creates a copy of the list. So when we do myList, pointed to this list of integers, then we do newList is equal to myList followed by the colon with this notation, right? When we do myList 0 equal to 10 and then newList 1 is equal to 20, as you can see, newList has 3 of the original content that was in myList, but because we also mutated myList to have 10 in the first index, then 10 will be at position 0. So this also makes a copy, and these two lists will not point to the exact same position in memory. Using lists as parameters and functions. When you pass a list as an argument to a function, you are passing a reference to that list. This means that the function can modify the list directly. The following function takes a list as an argument and adds a new item to the end of the list. So we define a function here called addItem, and it has a parameter myList, which is of type list. Here we declare a variable called newItem, set that equal to the integer 10, and then we do myList that appended new item. Right now, when we declare a list, set it equal to this list of integers, we can print the original list. Then when we pass the list to our function addItem, and then print the list again, right? The list added the value 10 to our list. So when we're passing this, right, to the function, it's passing it as a reference to that position in memory, and then we're mutating it at that position, but we're not returning anything. So this is mutating a list without returning a new list. Notice the function addItem does not have a return value. It only changes the list it takes as an argument. Again, this is how the code, what's happening in the code with a Python visualizer. This code doesn't return a new list. It just modifies the provided list. And by modifying it, just adds a new item to it. Global frame reference refers to the variables defined in the main function, whereas the addItem frame with a blue background represents the parameters and variables within the function. As you can see from the visualization, the addItem function refers to the very same list as the main function. Right? A list points to this position in memory, myList, and the addItem function points to the same position. The changes made within the addItem function also reflect the main function. Another way to implement this functionality will be to create a new list within the function and return that. So here, we define the same list that returns a new list, returns a list, right? So we create a list copy, then append to that copied list, and then we return it. right? So let's copy this and we'll put it in the Python playground. In fact, what we could do is to print ID numbers and then numbers 2. So now as you can see, right, the list that's returned from our add_item function is pointing to a completely different position in memory than the original list that we created. So that's what's happening in this code. Okay, editing a list given as an argument. The following is an attempt at a function which should augment each item in a list by 10. Define a function here called augmentAll. Takes in a list as a parameter, doesn't return a list, it doesn't return anything. Here we define a new list that is equal to an empty list. For item in my list, new list set append item plus 10, and then my list is equal to new list. So we go through this list, right? And then we append to our empty list that's defined within the function with each item in my list plus each item is incremented by 10. So if we had a list that has 1, 2, 3, then the first position will have 11, the second position will have 12, and the third position will have 13. Then we set the parameter, my list, equal to the new list. Now when we declare a new variable here called numbers, set that equal to this list, we print the list in the beginning, then we put our list through the augmentAll function, and then when we print, we get 1, 2, 3. Now why is that? Because even though my list is pointing to new list, this isn't being I don't know how to properly explain this. So here we're changing the reference of my list to where this new list is pointing to, right? But this change isn't reflected outside of the function. Remember scoping in programming, right? We made a change here to point my list to where new list is sitting at, but outside of our function, that's not reflected, right? We don't have access to that update. So that's why this isn't working. The function takes a reference to a list as an argument. This is stored in the variable myList. The assignment myList is equal to newList assigns a new value to the same variable. The variable myList now points to the new list created inside the function, and the reference to the original list is no longer available within the function. This assignment has no effect outside the function, however. Furthermore, the variable newList, which contains the new augmented values, is not accessible from outside the function. It is quote-unquote lost as the execution of the function finishes and focus returns to the main function. The variable numbers in the main function always points to the original list. The visualization tool is your friend here too. Please go through the stages carefully and see how the original list is not affected by execution of the function call. One way to fix this is to copy all items from the new list to the old list one by one. So once we append to new list, then we can go through we can loop through again and set each index in our original list equal to each index in the new list. So now my list still points to the same reference and now has those updated values. Python has a nifty shorthand for assigning multiple items in the collection at once. So here we have my list pointing to 1, 2, 3. Then we can do my list from index 1 to 3, set that equal to 10 and 20. So now, instead of being 1, 2, 3, 4, now it's 1, 20, 1, 10, 20, and 4. In the example above, a slice of the list is assigned values from another collection. As we know, a slice can include the entire collection as we do this. So we could have done it this way instead of doing it using a for loop. Actually, there's no need to create a new list within the function at all. We can just assign the new values directly into the original list, right? And then we can just skip all this extra fluff and just go straight to doing this. Okay, here we have our first exercise called items multiplied by 2. It says please write a function named double items. Has this parameter numbers, which is of type list. It takes a list of integers as its argument. the function should return a new list which contains all values from the original list doubled. The function should not change the original list. An example of the function at work. All right, so this needs to return a new list that is assigned to this variable when it's called. So we'll copy this. We'll go to Python. I already have the exercises opened here. Going to paste that in. Go here, define numbers, double items. And my list, which is of type list. And then we can do for item in my list. In fact, actually, new list is equal to an empty list. For item in my list, new list that append item times 2. Then return new list. Let's run this. There we go. And let's test that. There we go. Send that solution to the server. Let's open the model solution in the browser as well. And there we go. Did the exact same thing. They did this shallow copy instead of doing it like how we did here. They did basically this. So everything in my list is assigned to new list. And then instead of appending new items, they just went through doubled the double list and doubled each position in the list. So you can do it that way. You can do it like us, what we did here. Set that equal to an empty list like this, and both solutions work just fine. Here we have another exercise called remove the smallest. It says please write a function named remove the smallest, which takes a list of integers as its argument. The function should find and remove the smallest item in the list. You may assume there is a single smallest item in the list. The function should not have a return value. It should directly modify the list it receives as a parameter. An example of how the function works. So define a list here of integers, call this remove smallest function, pass numbers, and when we print numbers, then it will move the value 1. So let's copy that. Go to VS Code. Let me close these. Whoops, excuse me. Paste that there. Define a function called remove smallest. And we say smallest is equal to my list at position 0 for an item in my list. If item is less than smallest, smallest is equal to item, then my list dot remove smallest, whoops, excuse me, like that. So this dot remove function with lists will remove a specific value, right? It's not an index, but it will move a value. So Python will traverse a list for us here and then find whatever the smallest is and remove it. So let's run this. There we go. So our original list had the value 1 in it. We went through it, removed it, right? 1 was between 6 and 3. We removed it. And now numbers, again, we're not creating any new lists. We're not pointing to any new lists. Numbers now has the smallest value removed. So let's test that. Pass, and that solution to the server. Show the model solution in the browser. And they did it even smoother than we did, right? So you can use the min function with lists. It will return the smallest value in the list. And then you can just do numbers that remove smallest. So this is even better. But again, as I always say, I want to keep my solutions kind of very similar to the content that we're learning at the time. So that's why my answer was like that.